Alright, good afternoon. So let me finish this example before we start the exam. We talked about the spring in parallel. How can we find the equivalent stiffness where we have parallel system? Parallel system meaning that when you all springs they have the same deflection, something like this. So in that case, the stiffness K equivalent would be K1 plus K2. If you have more than stiffness, you are going to add them up, and you replace this system with the equivalent stiffness. This is a parallel. For series where we have the same magnitude of the force on the springs. So when you apply force or weight here, since it's a rope and height of the rope, you are gonna see the same amount of the force. We call it series, spring in series. So K equivalent, it's gonna be we can find the equivalent stiffness by using the series spring in series. Then we started this example. It's the crane machine. So there is a boom made of steel with a cross section of 2,500 millimeter squares. So A1 made of steel. And there's a cable BF. It's made of steel, but it's a cable with a cross section of 100 millimeter square. So there is a weight that we applied at point E. So we would like to model this one with a spring mass system. So if you look at this, we can say that we have mass here. AB, boom AB has mass. Also cable FC has mass inside of that. And at the same time, it's a rod which is going to be under compression. So it has a stiffness because it has deflection, and that is acting as a stiffness or a spring. Also the cable FC, it's going to have a stiffness a specification as well. But it's going to be difficult if we consider mass for AB. So since the mass of AB compared to the weight that you have here is small, you can neglect the mass of AB and FC and say they are massless, and we model them as a two spring. Just we consider the stiffness of cable BF and boom AB. So again, if you want to have more accurate analysis, we should consider the mass for A, B, and CF or BF. But to simplify the problem, we can neglect the mass for this cable and this spool. So for this one, we would like to find equivalent spring such that replace this one by this one. So then we can forget about the crane, just look at this simple mass and spring system. So the goal is finding K equivalent. Let's see if we have parallel system. For parallel system, if this when this point is moving with the magnitude of x, for example, these two should have the same amount of deflection, which is not correct because they have different stiffness. The deflection is going to be different. Is it the series? If you apply some force here, the magnitude of the force in these two would be different. So it's not series system, so we cannot use this equation or this one. So the method that we are going to use is we are using the energy method. The energy method in a spring says summation of potential energy in original system must be equals to the potential energy in equivalent. In equivalent system. So, for example, when you apply weight W, this is gonna move by deflection of x, for example, by amount of x. So point P is gonna move by x, or this guy is gonna extend it by the value of the x. So for a spring, when you make the deflection or compression with the magnitude of the x, the potential energy that you store in the system is going to be half of a stiffness, which is K equivalent, times x squared. So in equivalent system, the potential energy that we have is a half of K equivalent x squared. So this must be equal to the potential energy that we are gonna store in these two springs. So how can I find that? I should say if this mass or point B is moving by the magnitude of the x, how much compression I'm gonna make in this spring or in this boom, how much compression I'm gonna have in this one, so x1, x2. So if I know x1 and x2, I can say half of k1 x1 squared plus half of k2 x2 squared, it's gonna be equals to this one. So by using this equation, I'm gonna find K equivalent. So in many examples, what we are gonna do, we are gonna use the potential energy system approach to find equivalent stiffness. So this is a good example to apply this approach. Question on this?
You're neglecting gravity.
Pardon?
You're neglecting the potential for gravity.
Not gravity. I just compared this, the equivalent system, mass spring system, with the original one. I assume that when I add the weight to this, I'm gonna make some compression on this system. So this mass and spring is gonna be at this different location with the magnitude of the x. Okay, and how much would be the potential energy for this that you absorb? You are gonna store in this system is gonna be half of the stiffness times the deflection, which is x. Now this is gonna be equal to the potential energy of the original system, which is gonna be x1 compression in this spring, half of the k1 x1 squared, plus the half of k2 x2 squared. This is what we are going to do. The next step is finding K1, finding X1, finding K2, and finding X2. We looked at this example when a bar or rod like this, which is under axial tensile or compression. The equivalent stiffness for the bar or rod or cable or this boom is going to be A, the cross section, E1, the modular elasticity of the material of the component divided by the length. So if I want to find K1, which is this, is going to be half of, not half, A1 is 2,500 meters times E1 divided by L1. It's made of steel, so 207 10 power 9 Pascal or Newton meter square. L1. How can I find L1? I did it in this length is 3 meter, this length is 10 meter, and this angle is 135. So L1 square would be 3 square plus 10 square minus 2 times 3 times 10 cosine of 135. Cosine rule, I can find L1. So L1 would be 12.31 meter. So if I plug in the 2,500, I should change millimeter square to meter square, 10 power negative 6. 207, 10 power 9 divided by 12.3. It's gonna be not this one is A2. A1 is 100. Cable BF is A1. It's gonna be 100. K1 would be 1.68 mega Newton per meter. Mega means 10 power 6. So I have K1. What would be the X1? Just look at this and this. If point B is moving by X, which is the case, I would like to know how much compression I'm going to make in BF. So if this is 90 degrees, the compression is going to be this, which is X1. So if this is the X, the compression that I'm going to make on BF would be X1. So here I can find the relation between X1 and X. So X cosine of theta would be X1. Cosine of theta is going to be X1 divided by X. If I multiply cosine of theta by X, I will find X1. So what would be the angle of theta? This angle. If this is 90 degree, if I find this angle, this is gonna be 90 minus 3. What would be this angle? In this triangle, this is 135 degree. Write the sine rule. L2 divided by sine of phi, L2 divided by sine of phi would be L1 divided by sine of 135. I'm looking for this angle. Why do I need this angle? Because I can find angle of theta. 90 minus phi is going to be theta. So for that reason, I'm looking for angle of phi. So L2 is 10 meter. 10 meter divided by sine of phi equals to L1, which is 12.3 divided by sine of 135. So I can find phi equals to 35.1. So if this is 35, x cosine of 90 minus 35.1 would be x1. I'll keep this equation. I'm done with the first term of potential energy for the original system. Second term, half of K2 would be A2 E2 divided by L2. A2 is 2500, 10 power negative 6. E2 is the same material, made of steel, and L2 is 12 L2 is 10 meter. 51.75 meganewton per meter. What would be the relation between x and x2? If this is x, this is x2, if this angle is this angle. This is 135, this is gonna be 45. This is 90, so gamma is going to be 45 degrees. So if this is moving by value of the x, this is going to move by x2. And x2 cosine of 45 would be x. Now I'm writing this equation. Half of K1 1.68, 10 power 6, it's a meganewton, times x1 squared. X1 is this. It's x cosine of 90 minus 35.1 squared plus half of K2, 51.75, 10 power 6, times x2 squared. X2 is x times cosine of 45 squared. So this summation must be equals to half of K equivalence x squared. So if I expand this, it's going to be x squared cosine squared. Same things here, x squared cosine squared for 45. I can cancel out x squared from both sides. In almost all of the problems that you are using with the energy method, you should cancel out the variables that you have. Then you can solve for k equivalent. If you cancel out this half, then k equivalent would be this plus this, which is 26.43 10 power 6 Newton per meter. And this is the equivalent stiffness for this current system. So you can replace this one by this weight and the spring value of 26.4 10 power 6. In homework's problem, you might see some problems like this asking you to find the equivalent stiffness. You have three methods: parallel systems, series systems, and using the energy method. Depending on the problem, you should choose the proper approach. Question on this? And if you remember, the spring is it's a means to store the potential energy. So we use the energy method by equating the potential energy of the system in original system and equivalent. By setting up this equation, we could solve for equivalent stiffness. Mass is gonna be the means to show or represent the kinetic energy. So on Wednesday class, we are going to talk about the equivalent mass. For example, if there is a bar with these three concentrated mass, M1, M2, M3, which is rotating, what if I want to represent this with one equivalent mass? What should be the value or magnitude or amount of this mass to represent the same effect of the original system? So we are going to use the kinematic energy equation instead of potential energy to find equivalent mass. We will do it on Wednesday class. Question on this example. All right. So let's start the exam. And it's about what you have seen before in previous courses.